expression. Output voltage VCC minus RC times, remember this is IC. ISE to the power VBE over VT, that is actually your collector current, DC collector current. If you put VBE, total VBE, then this is a total collector current. Now you have done differentiation this year. Differentiation is basically rate of change of a value with respect to another value. So if we differentiate this expression VCE with respect to e to the power VBE over VT, then the final answer that you are going to get is this. Negative sign IC times RC over VT. So AV is the voltage gain. Voltage gain is IC times RC over VT with a negative sign. We have indicated what is that negative sign because this is a common emitter amplifier. Common emitter amplifier introduces 180-degree phase difference with respect to input. Or in other words, you give a positive going signal at the input of a BJT. At the collector, you will get a negative going signal. That's the meaning of it. Now, this term IC over VT, we have seen that before. That is called IC over VT is called transconductance. So if you put that down here, your AV is minus GM times RC. This is the explanation of what we discussed before. You choose Q point in the middle, you can have positive swing maximum with negative swing equally maximum. Okay. Now from this diagram, this is your positive swing that is possible before amplifier enter into cutoff. So the positive swing is basically limited by voltage drop across RC. Your negative swing is limited by amount of VCE. So in this BJT, positive swing is this much. Whatever voltage at the collector, all the way up to VCC is your positive swing. Once you reach VCC, then you enter cutoff. Negative swing is this much. Whatever voltage at the collector, all the way to voltage at the emitter, which is nearly zero. That is your negative swing. This is, if we get this much right, then we can play around. If you move this point up, or basically Q point up, you get reduced signal swing before entering cutoff. If you move Q point down, your negative signal swing will be reduced before entering saturation. The second point is signal swing at the collector is small IC times RC. Small IC times RC. Small IC is GMVBA. So always the signal swing, GM, VBE, RC. This is where we stopped in the previous session last week. Okay, voltage gain is rate of change of output voltage with respect to input voltage. So delta V0 over delta Vi is your voltage gain. Now, we have seen an expression for voltage gain, negative IC times RC over VT. So looking at the numerator, we can say voltage gain is directly proportional to voltage drop across RC. It follows that maximize the gain, we should use large voltage drop across RC possible. But given VCC, if VRC is increased, transistor will operate at a lower VCE. What's the problem with lower VCE operation? Going back to the diagram, lower VCE means negative signal swing is getting limited. Negative signal swing will be limited if you try to make gain very high, your VCE going to be smaller and negative signal swing will be limited. This is the explanation of the previous graph. In words, lower VCE means that bias point is closer to the end of the active region, low on the graph, which will not leave sufficient room for negative signal without amplifier entering saturation. Okay, what exactly it says? For this BJT, if the signal at the output is entering saturation, that is the negative signal swing that is causing the problem. In order to explain this, let me open LT-Spice. We have made use of, I think, this one. Yes. We have seen this before. Okay, I am going to put amplitude, say 100 millivolt. Going to simulate. That is your output. There is no clipping. Let me try to make it slightly more. Now only get one sine wave. Let's have 5 sine waves. There is no clipping now. Voltage at the collector is 7.94. That's like 8 volt. And the voltage at the emitter is 4. So the negative signal swing is possible. Voltage at the collector to voltage at the emitter. That is your VCE. Negative signal swing possible is 4 up to 7.9, around 4 volt. Okay. Now I am going to increase the value of RC to 4.7K. Remember, now what happens? Same amount of IC flowing, RC become bigger. So IC times RC is going to be bigger. We'll see that now. Voltage at the collector is 4.94, nearly 5 volt. That means supply, this is 12 volt, this is around 5 volt. 7 volt is across RC. There is only one problem. Voltage across RC is 7 and voltage at the collector is 4.9. Voltage at the emitter is 4.06. So the negative signal swing is from 4.9 to 4.0. Negative signal swing allowed currently is around 0.9 volt. That is why looking at this, see, positive is perfectly fine. Going negative from 0, it is swinging up to around negative 0.7. That's all it can go. Amplify, enter into saturation. So in the lab, while doing the experiment, you are getting a wave that is getting clipped on the negative side. It is saturation. Now, so understand at the output, if you are getting a negative clipping on the negative going signal, amplifier is entering saturation. Do you want to see how an amplifier is going to cut off? Let's go back and change that into 2.78. That was the original. I'm trying to make voltage at the collector very close to 12. So let me go and make that 1K. Okay. Now, after simulation, you will see. If you know the collector current, it's easy. Let me see. Collector current is 1.5 milliampere. So 1.5 milliampere passing through 1 kilo ohm, IC times RC is 1.5. Or in 12, voltage at this point is 12. Voltage at this point is going to be 12 minus 1.5, that is 10.5. You can see at the bottom left hand side, 10.49. Now, if you simulate now, you might see so-called distortion on the positive going side. I'm going to simulate it now. There is no problem there yet. Now, why is it that? Because the voltage gain is so small, signal is not going all the way up to the positive side. Now what we do to make it, to demonstrate clipping, it's simply going to increase this input amplitude into, say, 200 milli. You can see on the, look at the negative side, it is going very sharp. Look at the positive side, it is flattening. That is entering into cutoff region. Positive side is flattening. This is the beginning of distortion. Now, if you have anything more than that 200 milli, for example, let's make it 250 milli. Okay, I'm going to simulate. You can see the positive side is more and more getting round. The sharp side negative, it has no problem on the negative side. This is entering into cutoff region. If you increase your input signal, you will see more predominant effect. 300 milli. Simulate, you can see the positive side is flattening, flattening, flattening. More distortion on the positive going signal, indicating amplifier is entering cutoff region. Sorry, I wanted to increase it again and show you. I'm going to make it 500 millivolt simulation. Look at how is the positive side and negative side now. I'm going to simulate. You can see positive side is more and more getting flattening. If you increase your input signal much bigger, like 1000 milli, that is 1 volt, you will see a very heavy amount of clipping on the positive going side. You can see that now. Positive side is almost looking like a square wave. Time for questions. You can ask from this simulation side or even from the theory side regarding the Q point or even VTC. Yes. The point is with respect to this diagram. No, don't just other side. There are two sides. Which side? Positive going or negative going? Okay. The only thing that we did so far by changing the value of RC, or there is only one thing that I did. When I moved, when RC is made from 2.7K, that was the original value. When it made 1K, your Q point became somewhere on that side. So the first clipping, you observe that side. Negative supposed to go without a problem and come back. So the clipping happened on the positive side. That is the only thing happened now. Now, going back there, you are saying that why on the negative side also show some form of clipping. Okay, there is a possibility because your input amplitude was already 1 volt. So if you increase your input signal beyond limit, it can clip on the negative side and positive side. If you want me to show you that again, I'm going to make it 2 volt, amplitude 2 volt. It is going to make clipping on positive and negative side. You can see there. Okay, this is the effect of a transient wave. If you want to see it properly, I'm going to do one thing. I'm going to simulate it for 15 millisecond. And if you do 50 millisecond simulation, you will get 50 sine waves in such a small area. But I can show you what is going to happen. See, amplitude is becoming steady after a while, right? It is lifting up. Amplifier is getting stable around 30 milliseconds after simulation started. After that, amplitude is nearly constant, you can see there. The clipping on the positive side is still present. Negative side is not present. If you wanted to see it more clearly, what we can do is go into simulation. It is still simulating, I believe. No. If you want to see it very clearly, time starts saving the data. I'm going to keep it 45 milli. That means computer is going to work out, but after 45 milli up to 50 milli, computer is going to simulate. Then we are only going to get 5 millisecond. That is 50 milli minus 45 milli is 5 milli. You will get only 5 sine waves, and it is going to look very clear. See, negative side, there is no clipping. On the positive side, heavy clipping. I'm going back to the theory part. Again, this is to get a beautiful insight how a BJT amplifier is operating. And you can also play around with so-called, remember, we have designed quite a few BJT amplifiers using voltage divider, using two supply voltage. There are quite a few we made. You can make each of that in LT Spice and simulate. And that's a very interesting way of studying. Any other question? Okay, now we are going to move on. Small signal operation of and models. What we are trying to do here is small signal. We already defined small signal operation means the voltage between base and emitter. The AC voltage, DC voltage doesn't matter. That once biased, we are going to leave it. The AC voltage between base and emitter is very much less than VT. In that case, what is going to happen? Look at the second diagram here. This is a standard connection biasing a BJT amplifier. VCC used to bias collector emitter, and there is VBE used to bias base emitter. In this case, we only have DC connection and another DC connection. Now you can see there is a DC base current, there is a DC collector current, and there is a DC emitter current. All the currents are DC. What about the voltage? VCE is also DC. Now, looking at the first diagram, here we added an AC signal. So DC is still present. We added an AC signal. Now you can see your base current is a total base current. There is a DC and an AC. And the collector current is a total collector current. Emitter current is a total emitter current. And your output voltage, VCE, has a DC plus AC. Okay, the small signal operation basically what we are going to do is from this diagram, assume that you are going to short circuit. Assume you are going to short circuit that battery, and you're going to short circuit this battery. All the DC batteries are short circuited. Remember, this is a concept level thing. Okay, what can happen now? This total collector current becomes small IC, that is AC collector current. this emitter current will become like this, and the base current become small IB. So if these two batteries are short-circuited, that is your VBE is short-circuited and your VCE is short-circuited, all the currents become AC collector current, AC base current, AC emitter current. Are you able to grasp that concept? This is called small signal operation and models. We are going to short circuit all the batteries. Okay, of course, when you short circuit a battery, voltage across the battery is zero and it cannot produce a current. But we are going to assume all the batteries are short circuited and your VBE is still present. Then what could happen? And that kind of an assumption is called small signal operation. It's not that everybody is going to, this is a conceptual way of seeing the effect of short-circuiting the batteries. Okay, the first effect of small signal operation, we have seen quite a few already. That is where we started today. There are three: VBE less than VT, then GM is IC over VT, and small signal collector current is GM-VBE. These three are present. What are the other effects? The other effects are, okay, before getting in there, the first chapter that we studied, let me use my camera now. In the very first chapter we did this year, how an amplifier is made. An amplifier is represented this way. I don't know why it's going out of focus. Better. An amplifier has something called an input resistance then amplifier has where it generates a gain, AV times VI. What is VI? VI is the voltage across RI. Amplifier has an output resistance that is called R0. This is how an amplifier is made. Now, when we have a signal source, we are going to put the signal source, AC signal source called VS. Every signal source is coming with an internal resistance called RS. The signal source together with RS, it is not a part of the amplifier. And this is the output of the amplifier. We connect RL. And across RL, it generates a voltage V naught. This is one of the very first thing that we learned this year. Now, AV times VI, we are going to leave it. Let us try to find out what is this RI when it is a BJT amplifier. And later we will see what is this R naught for a BJT amplifier. Then we will see what is this AV times VI for a BJT amplifier. So currently we are looking at RI of a BJT amplifier. BJT. Okay, I'm going to close this one. Going into the slide. Okay, a BJT has two input terminals. That is base and emitter. That is this one. Signal is always connected between base and emitter. In this case, your emitter is at ground. In the second case, base is at ground, but VBE is connected between emitter and base. So we are looking at input resistance in both cases. So in this kind of a connection where the emitter is at ground terminal, what is ground terminal? It is called common terminal. Remember, we defined while we did three different modes of operation, three configurations of a BJT, there is one terminal used as a common between input and output. Sometimes we use emitter as common, sometimes we use base as common, sometimes we use collector as common. Two of those things are already here on the screen. In this case, emitter is common. Okay. Input resistance looking at the base. We apply a VBE between base and emitter. This VBE makes a current IB. Now, if you take VBE divided by IB, then we can find input resistance parameter of a BJT looking at the base. Input resistance looking at the base, and it is defined like this. It is given a new name. Input resistance looking at the base is going to be called as R suffix pi, R pi. It is defined as VBE over IB. And there is a formula also given. R pi is VBE over IB. You can either find beta over GM or VT times beta over IC. If you know GM already, then beta over GM will do. If you did not find GM first, then this is what we normally use. R pi is VT times beta over IC. That is, remember this, input resistance looking at the base is R pi. Second case, input resistance looking at the emitter. You can see there is a VBE, and you can see there is an emitter current, small signal current. So VBE divided by the current is defined as RE. And it can be found like VT over IE, and which is going to be nearly same as 1 over GM. Why is it 1 over GM? because IC divided by VT is GM. So IE and IC are nearly same. That is why we put an approximately sign there. So RE is the input resistance looking at the emitter. So we have seen two different ways of finding. No, I wouldn't say two different ways of finding. I would say a BJT amplifier, depending upon how you connect, you will have two different input resistances. If the emitter is on ground, you look at the base for the input resistance, you can find R pi. If base is at the ground, you are looking at the emitter, you find input resistance called RE. Okay. Now, on practical case, what do you need to remember from the slide? I would say everything that is here needs to be remembered. R pi is Vt times beta over IC. Re is Vt over IE, or rather equal to 1 over Gm. And we can also make a relationship between R pi to Re. R pi is Re times 1 plus beta, or if you already know R pi divided by 1 plus beta, you will get Re. So all these things under the shade, this is something that you need to be remembering. You won't get that from there is no formula sheet, but these things you need to remember. While we were working out on power supply problems, I would be recommending that you don't need to remember any formula. You need to remember very few things. Primary voltage of a transformer to the secondary voltage, primary voltage divided by turns ratio. From transformer secondary voltage to peak rectified voltage Vm, that is RMS to peak conversion, V secondary times square root of 2 minus diode voltage. And how do you work out VDC in a power supply? Vm minus P ripple peak to peak divided by 2. That you need to remember from the slide. What you need to remember in the power supply chapter, V ripple peak to peak equals IL divided by 2FC. That you need to remember. So that's the only formula that you need to remember in the power supply chapter. While we reach BJT, we need quite a few things that you need to remember, or I would say from my slide, if you see something that is under the shade, background shade, like this, anything coming under the shade, it is a formula that you need to remember. Time for questions. Internal resistance or input resistance? You wouldn't need to. That you will understand much later, not now. Currently, this 2 is good enough. As we work out more problems, we will understand that much easier. But even for a common collector, R pi is going to remain same as common emitter. Now, that's why I said we are trying to explain it conceptually. It is only conceptual way of explaining. How can you see small signal base current, small signal collector current, and small signal emitter current? Because we need to understand that conceptually. How is it possible? Otherwise, without understanding the conceptual way of understanding, because the entire small signal model is developed based on this assumption that all the batteries are short-circuited. All right, we are going to move on to small. We have seen defined R pi, that is input resistance looking at the base, RE, input resistance looking at the emitter, and there is a relationship between R pi and RE. This is like saying base current equals, emitter current equals base current times 1 plus beta. We have seen it. This is same thing, repeating again for the impedances. Okay, here is everything that you need to remember. Amplifier with only signal components. This is the pure small signal model. See, collector is connected directly to the emitter. There is no VCC. Between base and emitter, there is a VPE. Now, it is going to generate first IB, small IB. This is only signal base current. And signal collector current is GM VBE. Remember, we defined this. In fact, in the previous class, we saw that beginning of today. And small signal collector current is VBE over RE. So everything we learned so far present here in one slide. We defined R pi today. R pi is VT times beta over IC. And RE we defined today. RE is VT over IE. So IC we defined before, small signal collector current, GNBBE we defined in the previous class, and your output signal is basically VCE in this case, because at the emitter there is no resistance. Formula 1, IC over VT. R pi is VT times beta over IC. RE VT over IC. Okay, I must put approximately. Why? Because I used IC. Small signal collector current, GMVBE. Small signal base current, VBE over RP, R pi. And small signal collector emitter current is VBE over RE. Very rarely we are going to use this two, and all other things we are going to use almost regularly. Okay, amplifier circuit with DC sources VBE and VCC eliminated, that they are short circuited. The purpose is only to reveal small signal values. Thus, only the small signal components are present. Note that this is a representation of the signal operation and not an actual amplifier circuit. This is a representation. When it is a representation, the common name we use is called small signal modeling. Okay, with this, we are going to stop for now, and in our next class, that is tomorrow. See, I have to tell you one thing. We have an engineering council visit, accreditation visit, that is happening tomorrow and day after. The lab is going to run as usual. And the theory class, because the engineering council wanted to, they demand consultation from the lecturer. And what time it is going to happen, I am not sure. But for theory, labs are going to run normally. It is not going to be disrupted anyway. Theory class may be disrupted or may not even happen tomorrow. Okay, thank you very much.